a monotone increasing sequence. AN. What does that mean? It means that AN is less than AN plus 1, which is less than AN plus 2, and so on. That is bounded above. That is bounded above, meaning AN is less than M for some M, and for all N. So if such a sequence is bounded above, then it converges. Okay. Right, and similarly, if AN is monotonically decreasing, and bounded below, so decreasing, increasing, above, then it converges. All right. Good. Let's prove this. From last time, the set AN n bigger than 0 is bounded above so from last time we proved the least upper bound principle. So by LUB, the supremum of S, we call it L, is finite. It exists. We'll show that, want to show that AN, that the limit of AN is L. So that's what we'll show. Okay, so how do we do this? We will use the epsilon definition. Remember, the limit definition is that for every epsilon, there exists n such that AN minus L is less than epsilon for all n bigger than n. Okay, so fix epsilon. Then by the epsilon definition of the soup, of soup, there exists an element A and epsilon in S such that L minus epsilon is strictly less than A and epsilon, which is less or equal than L. So, any questions? Okay. Right. Right, but we have monotonicity, but by monotonicity, this is the same as L minus epsilon is less than A and epsilon, which is less than AN, which is less than L, for all n bigger than n epsilon. And that's it. So we showed that we showed the following. We showed that this is less than L A minus AN, less than epsilon, for all n bigger than n epsilon, which is just the limit definition. For the decreasing case, so yeah, is that okay? For the decreasing, let Pn to be minus An, and repeat the proof, the above proof. All right, so let's do an example. So the sequence E minus En square is decreasing monotonically to 0. So if you like, this is 1, 2, and this is E minus N square. Okay. And is bounded below by 0. And is bounded below by 0. So by MCT, AN converges to some number L. So AN for some L. But yeah, we can see that this is just the infimum. So AN will just converge to the, so if we repeat the proof, we know more. We know that in fact AN converges to the infimum, which is just 0. Is that okay? Okay. So a more general fact is if an is of the form f of n, where f of x is bounded above, and is monotonically increasing. Meaning that, so f of x is less than f of y. Or more weakly, f prime of x is positive if you're differentiable. If that's the case, then by MCT, the limit An exists. So all right, so here's another theorem from the book. It's called the nested intervals. Suppose that you have a collection of intervals. Are intervals A and Bn that are nested, meaning In plus 1 is within In. So this is An, Bn. And then somewhere inside you have the next guy. Right, and they're non-empty. So non-empty. Let me hide this. Non-empty just means An is not Bn. Then, if you intersect them, so then their intersection is non-empty, meaning I1 intersect I2 intersect so on is non-empty. So you have all these intervals, and then as you keep going, there's a limit. Non-empty. maybe I should do a simple example first. Let in equal 0 plus 1 plus 1 over n. So that's that. These are nested, and their intersection is equal to 0, 1. Can the intervals be open? No. So let me do an example. Y open, Y closed. So take same guy, but open. Let me see, I have to think. Let's work. Yeah, let me think about it. I have to think about this. I want to give you a good example. Yes, I have to think about it. I can't just come up with it. Okay. So yeah, I will put it in the notes. Yeah, you get the empty. That's right. Yes. So yeah, that example is better. Thank you. I put -1 over n, but that wasn't good. Yes, that's exactly right. Thank you. Thank you. So y closed. Indeed, I take open 0 and 1 over n. If you intersect them, going up to n is equal to 0, 1 over n. And then if you take limits, you get the empty set here, and here you get the whole thing. Yes. Thank you, Eric. Good. So the sequences an and the bn are bounded above and below. by the biggest interval, I1, meaning AN is a lower bound, and B1 is the upper bound. Right. So by LUB, right. Okay, so you have this, but there also we will apply MCT here. Why is that? By nestedness, of intervals, we get AN is less than or equal to AN plus 1, and BN plus 1 is less than or equal than BN. So the picture is AN plus 1, BN plus 1, BN. So it goes this way, goes that way. So now we have the two conditions. We have the bounded above and below, and we have the monotonicity. So MCT says that AN converges to some limit L1, and BN to some limit L2. Is that okay? Why is it AN? What's going on? Why do we need to express? I'm just proving it, Levon. I'm proving why is it empty. Then it doesn't. That's right. Yeah, we want them to be non-empty. Yeah. Okay. So what's the question? Why do we need to express as a limit of big N? Let me go back. So here I'm proving. So why is this empty? Use a limit definition. Since 1 over n converges to 0, and 0 is not in the set. So this requires proof. It's tricky. So why is this true? Try to prove it. And this inequality, indeed, this is because they're non-empty. Okay. Okay. Good. Okay. Good. Thank you. Right. Claim. L1 and L2 are in the intersection. And so it's not empty. So, and that will prove it. So, you know, right, and it's not empty. I don't like the way I wrote it. So, okay, let's see. And so is non-empty. Okay. Yeah, so we prove this by contradiction. Suppose proof by contradiction. Suppose not. Suppose L1 and L2 are not in it. Well, I just need to do one of them. I don't have to do both. So suppose, suppose L1 is not in here. Okay. What does that mean? That means that there exists n such that L1 is not in IN. Why is that? Because if it's not in the intersection, it must not be in one of them. So if it was in all of them, it would be in it. So there exists at least one, call it IN, so that L1 is outside. So it's not in here. If it was in for every n, it would be in the intersection. So there's just at least one, so that it's not in. Good. But by nestedness, L1 not in IN means that L1 is not in IN plus 1, which contains IN plus 2, so on, which means that L1 is not in IN for all n bigger than n. If n is still non-empty. No, if the endpoints, right. So, yeah, we mean non-empty interior. But let me see. So yeah, now that I look at it, we don't actually need it. That's a good question, Nick. That's right. No, you're right. You're right. We don't actually need it. They can be equal. So let me add this. That's a good point. If AN is equal to BN, then IN would just be a singleton, and the same proof follows. So we don't actually need. Yes, thank you. I will add that you don't need strict inequality. Nick, is that okay? Nick? Does it have to be closed? Yeah, that's the main thing. So it has to be closed. Otherwise, we gave an example where if you have open, the limit is empty. So Shirley asks, does it have to be closed on both sides? And the answer is yes. Because of the example we gave above. Good. Okay, so here, this will give contradiction. So let me see. Since IN is closed, there exists epsilon naught, so that L1 minus elements from IN are bigger or equal than epsilon naught. So this is the picture. This is AN, this is BN. Suppose L1 is here. This is epsilon naught. Okay, so there's a positive distance. If there was no positive distance, then if epsilon naught was 0, we will get L1 equal to AN, which is a contradiction, which contradicts not in IN. Okay, so we're almost there. Okay, but AN converges to L, which means what? So for epsilon, I don't know, equal to epsilon naught over 2, you get sum n. There exists n tilde bigger than n, so that for all n bigger than n tilde, L1 minus AN is less than epsilon, this is epsilon over 2. And this contradicts the following. So we showed that L1 falls outside IN for all n bigger than n. But then you're telling me that the endpoints are epsilon close. And so that's the contradiction. So what you showed is epsilon naught over 2 is bigger than L1 minus AN, which is bigger than epsilon naught. So you got 1/2 bigger than 1. Any questions? Solid be IN plus 1 contained in IN minus 1. It's contained in IN. Did I write something else? Yeah, I'm not sure what, yeah, Levon, that's exactly it. Did I write something else? Yeah, like inside here you have IN plus 1, IN plus 2. That's right. Levon? Okay. Oh. Good. Right. All right. So let's do a One example from the book. So, okay. Suppose you have the recursion. So you have a sequence. AN satisfies AN plus 1, five plus AN, and it starts from AN equal to 0. Want to show AN converges to L, where L is the solution to this quadratic equation. And you can find it. I think it was like one. Okay, I don't remember exactly the solution. I think it was like plus minus square root 2 or something, square root 3. We know AN is in, so AN is the endpoint, Bing Yao. So how do we know AN is in the interval IN? AN is just the left endpoint. By definition. Okay. Right, so we want to apply MCT. So we want to apply MCT. We need two things. We need bounded plus monotonicity. So let's start with monotonicity. I want to show that this is less than, that AN is less than AN plus 1, which is less than 3. So we have increasing, and we have bounded above. So then we can apply MCT. So let's see. We'll prove this by induction. The base case is easy, so base case. We have A0 is 0, so that's fine. Then we have that A1 is equal to square root 5 plus A0, which is square root 5 plus 0, which is like 2.3 something. I don't remember exactly, but it was less than 3. So that's the base case. Now do inductive hypothesis. Meaning you assume Pn and you want to prove Pn plus 1. So assume that 0 AN minus 1 is less than AN is less than 3. Prove it for n plus 1. write it. So 3. Right. Good. So an plus 1 is equal to square root 5 plus an. By the inductive hypothesis, this is less than an minus 1. But then by definition, this is an. So that's good. And then what's that? And then for the upper bound, this is less than square root 5 plus 3, which is square root 8. So 2 square root 2. And you get the same bound. So we know, yeah, we're proving it. We prove that it's bounded by 3. Oh, you mean for the base case, or? For the base case is this, and then we use the inductive hypothesis to get this. Yeah, so we're doing, I don't think I mean how do we find the 3? Well, I mean, first of all, 3 is not sharp, so that's one thing. And how we figure out the 3 is that we know A0. So we have A1 is equal to this. And then this is A0, right? Which is square root 5, and you can compute this. This is like 2.3, which is less than 3. So that's how so the 3 came from the base case. All right. What else? Yeah, it could even be bigger. Like, it's an educated guess. That's right. So we just made an educated guess. You can have 5 or 4. MCT just says bounded above. It doesn't have to be a special bound. Good. Xin Yu, is that okay? So any bound will, okay. Right. So MCT tells you, says that AN converges to L for some L. So now here is tricky, right? It's not easy to find the infimum. So here is tricky. It is tricky to find the supremum of AN. But what saves us, well, we can use the recursion, but we know AN is equal to AN plus 1 is equal to square root 5 plus AN. Now take limits of both sides. So take limit. And that tells you what? It tells you that L is equal to square root 5 of 5 plus L. The last step will be, no, we want a uniform bound. So that's right, yeah, since it's less than, yeah, but then we're trying to prove, so the question is, what's the upper bound? We're trying to prove this. We're trying to prove this for all. Yeah, we're trying to prove this for all n. Okay. All right, so let's take a small break, 5 to 10 minutes, and then I'll start again with subsequences. So I'll stay here for questions, but feel free to walk around. Something. So I'll be back in 5 to 10 minutes. So I'll be here, but you can do your stuff. So I can answer questions or anything you like. Right. Do we have office hours this week? So I need more. Only 6 people went to Survey Monkey to answer. So I'm waiting for more people to tell me their availability, and then we'll have office hours. Definitely next week. But since your homework is due this week, I should have some office hour. Yeah, I was gonna say. So since we have a homework this week, I should have some office hour. So I mean, I'll go check what happened at Survey Monkey, how many people answered, and we'll have a temporary one this week. And I'll wait for more people, then we'll change it back next week because I want to get more people to reply. So this week, yes, we need to have an office hour. So I'll announce one soon once I see the feedback from the survey for this week. Is that okay, Levon? So wait, there was another question. Proposition 2.8. Well, I don't know. I mean, feel free to post on Piazza. I'm sure other Bing Yao. I'm sure other students can help too. It's not a very difficult proof. So post your question on Piazza, and if no one answers, I'll come answer as well. Bing Yao, yeah. It's not very difficult. If you have a particular question, you can let me know. We are learning. That's right. Dedekind is an alternative proof. I'm following Terence Tao and the textbook. So, and the reason is because Cauchy sequences is actually more used than Dedekind cuts. So if you end up going more into math, you will see Cauchy sequences more often. Yeah, they're different things. That's right. Can we use 2.8? Yes, there are two alternative ways to construct them. That's right. So no, I would like you to use to prove. Um, so yeah, don't use proposition 2.8. As I want you to see if you can write down the argument. Part of the homework exercise is for you to rewrite the proof to make sure you understand it. So, and it's not that long. It's 2 lines. So you can write down the proof, make sure you understand it. So yeah, do not use the 2.8 directly. Try to write it down and see if you understand it. Yeah. Are we use no? I mean, the question is to prove that, right? So are we allowed to use the density of the rationals to prove the density of the irrationals? So no, you have to. That's part of the homework question. You have to prove that they're dense. Meaning that you can approximate by terminating and repeating decimals. Is that okay, Danny? Oh, for problem. Oh, I'm sorry. Yes. Sorry. For question 2, but can we use question 1? Yeah, of course. Yes. Within the homework, you can use questions, but not otherwise. When do quizzes get released each week? So you have a calendar. You can see all. I'm not sure what you're able to see, but it should say, I think it's on Thursdays that we release it, and it's due on Sunday. Joseph, so it's like 4 days. Yeah, but I'll check. Yeah, it's always on Thursdays. right. Is it better? Quercus, always use Quercus for emails. And because I'm getting some repeated emails, sometimes I just make an announcement. Because I usually get repeated emails, same question from different students. So yeah, on syllabus, yeah, I say to use the Quercus. Between the homework, I don't know what you mean. It's the same thing. Like sometimes I use no, like I mean, I don't know. It's not there is no distinction. Yeah, they're all graded. That's right. Exactly. Sharp. Yes. Okay. All right. So subsequences. Right. So here's a simple example. Suppose you have the sequence the following. So 1.1, 0.1, yeah, 1.01, 0.01, 0.01, 0.01, and so on. So let me plot this. It's kind of weird. So this is 1.1. This is 1. This is 0. And it goes like this. So this is 101, 1001. And then we have another one from 0.1, goes down like this. So this is AN. Okay, so clearly, AN doesn't have a limit. Right, so because it alternates, it keeps alternating between 0 and 1. But it has convergent subsequences. but the sequence is 1, 1, 1, 0, 1. So this is Bn, and this is Cn. They converge to 1 and 0. And these are sequences are subsequences of AN. So we have that Bn are the odd multiples, and Cn are the even ones. So odd, even. So A2n plus 1 goes to 1, and A2n goes to 0. But AN does not converge. Is that okay? So, can I write the decimal expansion? Yeah, I mean, this is in the book as well. Sure. It's the same thing. There's no difference. Are we counting 0, 1, 2? See. No, we're counting. Yeah, that's important, right? So here we mean. So this is A1. This is A2. This is A3. Not from 1. Chen Li, is that okay? In that case, Bn should be bounded by B by 2n minus 1. Am I saying something? Okay, let me see. Maybe I'm making a mistake. Let's see. What do I want to say? 2 plus 1. So yeah, let me make it clear what we mean here. So so this is for n. How do you say this? So this is 0. So Bn starts from 0, and Cn starts from 1. Yeah. Okay. Because then you get 1, A2, 1 plus 1, which is 3, and then A5, and so on. And then this gives A2 times 1, A2 times 2, A6, So definition is subsequence of AN is a sequence ANK with AN1, AN2, AN3, so on. And you have N1 is less than N2, less than N3, and so on. All right, so now we'll prove the main theorem, 4.7, Bolzano via stress. Every bounded sequence has a convergent subsequence. Okay. So remark, what are we saying here? MCT says that bounded plus monotone, so above increasing, gives a limit convergence. Right. Bolzano says bounded above and below implies convergent subsequence. So this is a more general result. It's more general. Or general assumption but weaker conclusion. Because as you see above, because as in the example, AN, yeah, the mother sequence AN, even though bounded, it might not converge. I don't know. Another more simple example is an equal to -1 to the n. So again, this is it keeps jumping back and forth. And a2n plus 1 is -1, a2n is 1. So these converge, but the mother sequence does not. Good. So let's prove this. So again, we want to prove that every bounded sequence has a convergent subsequence. So we'll use MCT and nested interval. All right. Okay, I'll split this in steps. We have bounded. And so S, the subsequence is contained in this interval. Call this I0. Next, split I0 into two half intervals. So -m and 0, and 0 and m. Let I1 be the half that contains infinitely many of an. So what's the picture? You split it, and now in at least one of them, infinitely many of an will be inside. So let's say they're here. You could have them in here too, but at least in one of them, there's infinitely many of them. Okay. Good. So yes, call that sequence, call that subsequence B1K. So if we go back to the example, what we did here is, we had these guys and we had these guys, 0.1, 1.1, and we just picked one of the intervals. So back to the example. M is, we can make it, what do I want? I want to split it here. I'll make M is 2. So we have 2 and then right, okay, good. So take I0 to be 0, 2, and then take I1 to be 0, 1, because it contains infinitely many points of AN, namely 0, 1, 0, 0, 1, so on. Do we have, no, you can split, the question is, do we have to split the interval in the middle? The question is, no, you can split it any way you like. Don't both intervals, that's right, yeah, they contain infinitely many points. So I1 contains of both, but I'm just saying what my first choice is. Then as we go deeper, the upper sequence will disappear. Very good point. So the question is, don't both intervals contain infinitely many points? Yes, that's in I0, in I1. Yeah. Now I2, they will disappear. Continue this process. To get nested sequence, nested closed intervals. IN plus 1, IN, I0. And right, and yeah, and each one of them. So let me say this. And B and K is contained in the IN, and is the subsequence. In IN. I know these are also satisfying monotonicity too, but we don't need it. So. Okay. So, but the lengths are decreasing. Okay, no, so let me, 1 second. So by the nested intervals lemma, the intersection is non-empty. Meaning, i.e., there exists L inside that intersection. Okay. But the lengths are decreasing. Lengths are decreasing. Why is that? So we have in plus 1 is less than in over 2, and so on till you get I0 over 2 to the n plus 1, which is m over 2 to the n. Okay. So what does that tell us? So that tells us that, so since L is in in plus 1, and Bn plus 1k is in in plus 1, we get L minus Bn plus 1 is less than 1, less than m 2 to the n. Okay, good. So we're almost there. So want to show that Bn, the diagonal sequence, converges to I want to show, let me see. Yeah, I'll call it too many notations. I want to show A and K converges to L for some NK subsequence. Okay. Fix epsilon positive. Then choose n large enough so that m over 2 to the n is less than epsilon. All right, so from star, we get L minus Bn 1 is less than 1 m2 to the n, which is less than m2 capital N, which is less than epsilon. Okay, and B1n is the subsequence. So the subsequence will be Bn1 for n starting from 1 to infinity. Is that okay? All right. So that's it. Okay. All right. So let's do an example. If you have any questions, just let me know. What is capital N? Good. Yeah, I can make a concrete choice. So let me see. I have to solve this equation. So m over epsilon log 2 is less than n. Okay. So let n to be the log 2 of m over epsilon plus 1. Pisman, is that okay? Pisman? Yeah. Why is it n instead of n plus 1 for the subsequence? Why is it n instead of n plus 1? I see. Yes, you're right. By star is n plus 1. Thank you, Levon. Thank you. That's a very good point. Yes. Levon, is that okay? Thank you. All right. So it's example 4.8. 2.7.I. Okay. So I'll state the question. It says, suppose you have a sequence is a sequence in R with the following property. So, and LK converge to L, some L. Okay, let me say a different one. So, and LK such that LK goes to L. Suppose they have the following property. If for each K, we have a subsequence. There is a subsequence of xn. I want to write this nice. Yeah, so there is some subsequence k of n that converges to Lk. Okay. Show that there exist subsequence of xn, I don't know, bn, such that bn, the limit, converges to L. Okay, so you have Lk, and you get a further subsequence L. So let me draw a picture. So you have x1, 1, x1, 2, x1, 3 converges to L1. Then x 2, 1, 2, 2, 2, 3, 2, 4 converges to L2. X 3, 1, 3, 2, 3, 3, 3, 4, L3. So this is the k equal 1, k equal 2, k equal 3. Okay. And then we know that these guys on the right converge to L. And our job is to figure out some subsequence subsequence, not necessarily the diagonal. I don't want to write diagonal. Could be something else. That converges to L. Okay, so that's the idea of the proof. So you have all these subsequences converging this way, and then you can find a guy that converges to L. This is called the Cantor diagonalization argument. All right. What's the strategy? The strategy is for each k, to pick an element xk and k that is close to Lk. And then show that they converge to L. All right. Good. All right, let's start. So for k equal 1, by the limit definition, by the xn for epsilon equal to 1 over 2, there exists n1 such that x1n minus L1 is less than epsilon for all n bigger than n1. Okay. So the picture is you have x11, x12, x13, so on. They converge to L1, and you pick the tail. That is that satisfies, that is 1/2 close. Okay. All right. So same by the limit x2 and L2 for epsilon equal to 1 over 2 to the 2, there exists n2 such that x2n minus L2 is less than 1/4 for all n2 bigger than n, for all n bigger than n2 bigger than n1. So let me draw the picture. X11, x12, x13, so on. We form the tail, goes to a 1, x21, x22, x23, and then we pick a further tail. So x2 and 2. Okay. Is that okay? Okay, I think you get the main idea. For the mth step, by limit of n goes to infinity of xmn, for epsilon equal to 1 over 2 to the m, there exists nm bigger than nm minus 1, such that xm n minus lm is less than epsilon 1 over 2 to the m for all n bigger than or equal to nm. Okay. Claim. Claim. A of m defined as xm nm is the desired subsequence. Subsequence. What do we mean by that? I mean, it's the sequence converging to L. Okay. All right, so fix epsilon as usual when you want to prove limits. Since Lm converges to L, you can find there exists let me call it N0. N0 large enough so that Lm minus L is less than epsilon over 2 for all n bigger than N0. Good. So that's one. And then second, pick n epsilon over 2 large enough. So large enough. So that 1 over 2 n epsilon over 2 is less than epsilon over 2. Okay. All right. So together, by taking m to be the maximum of the two, so take m to be bigger than both, we find the following. So first you do triangle inequality. Let me do the middle step. So you subtract and add Lm. So add and subtract. Then use triangle. Then use a triangle inequality. To get this. All right, so for this guy, we have from above that this is less than epsilon over 2. And this guy is less than 1 over 2 to the m. Okay. Okay, so what do we have here? We have 1 over 2 to the m plus epsilon over 2. By monotonicity, this is less than 2 to the n epsilon over 2 plus epsilon over 2. And I think you understand this is less than epsilon over 2 plus epsilon over 2, which is just epsilon. So let me repeat. So here we use the definition AM equal to XM NM. Here we used m is bigger than n epsilon over 2. Here we use the definition of n epsilon, and then we get epsilon. How did you pick epsilon 1 over 2 and so on to verify the sequence? So how do I pick epsilon? Yeah, so the pattern is we want this upper bound to go to 0. So the base case is 1 over 2. Then next step is 1 over 2 to the 2. And so here we have that this bound goes to 0 as m goes to infinity. So there is nothing special on how we choose epsilon. You just need something that goes to 0. So let me write this. So remark, there's any choice of epsilon m going to 0 will have worked. We picked epsilon m equal to 1 over 2 to the m just due to the monotonicity. Monotonicity. But there's nothing special about it. Another choice is em equal to 1 over m. So there's nothing special about that. Binging, is that okay? I mean, the class is over, so I will just keep answering questions because I see the clock is 1. So I will just stay here and keep answering questions. Okay. To verify the sequence composing of the tails of the initial subsequences. Yeah, so Danny, that's a very good question, and that's why we this is very important. That's why we picked nm to be bigger than nm minus 1 to have nested subsequences. Danny, is that okay? Yeah. Could you please clarify what AM is? I don't understand. Yeah, good. So, good. So from the M step, we got this statement, right? And this is true for all n, including the nm. So, so let me write it here. This is also true for nm. Right? So, Bisman, Is that okay? Okay, let me see. What else can I say? Maybe I can go to the beginning. So, yeah, let me draw a picture again. Good. So what happened? So we had some subsequences. We had x11, x 12, x 13, and so on. And it goes up to x1n1, x1n1 plus 1, and it goes to L1. And same, but we pick it further to the right. And again, further to the right for the next guy. And why do we pick these guys? Because like we said, at the nth step, the distance. So this is LM, and this is XM, NM, and then you have the other guys. This distance here is 1/2 to the m. So they're very close to I don't like this picture. Okay, let me do L1. I'll do L2. So for L2, the distance is 1/4. And we're saying that x2 and 2 is inside. x2 and 2 plus 1 is also inside. So what else am I saying? And yeah, so that we made a choice of a subsequence that converges to the limit point of the limit points. L is the limit point of the limit points. LK. Okay, good. Good. So for Levon, when we pick the integer part A0, yes, but why does this imply A0 is not an upper bound? Because X0 is an element of the set. Well, okay, let me say it differently. Right. No, Levon, you're right. I used bad phrasing. So I should have said A0 is not necessarily the upper bound. It could be that X0 is the upper bound, but A0 might not be the upper bound. But A0 plus 1 is definitely an upper bound. So Okay, yeah, I will add this word. It's not necessarily. Also, can we express L? Yeah, that's how we defined L, exactly. Yeah, L is equal to A0, A1 by Y. That's how we constructed L. That's our construction, and then we proved that this construction works, meaning that it's a list upper bound. It's an upper bound and also satisfies the epsilon definition. Why can it be a limit? Why? Oh, that's right. So to convince yourself for that, you can write it uh, as a decimal series. And then you see that the decimal series converges because it's upper bounded by M. So the set M is upper bounded. So how do you say this? Yeah, let me write a little bit on this. So ln is equal to um, 0 to n of 10 to the k. But all these guys are bounded by m because because S was bounded above. I will add this on the notes because that's a good point. I have to clarify this. So this was set was bounded above, so there is an M. So if you like, how do you say this? Well, there's many ways to say this. So ln is less than, how do you say this? I mean, the question is, do you have ln going to L? Because L minus ln, is equal to the subsequence, to the tail sequence, I mean. And this is less than 9 n plus 1, 10 to the k. And this goes to 0, to 0. Levon, is that okay? Bin Yao, can we use that supremum of this? So, yeah, you should prove these things because we still haven't, so we're learning. Supremum and infimum, we just defined it. So, yeah, try, write down carefully the statements. If they're in the book, copy what is it in the book. So, I just want you to write down carefully what you're working with for practice. Bin Yao, is that okay? But you used the first one in the proof of 2.8. Right. Yeah, I will, yeah, well, right. So you have to prove it, that's true. But I will also go add that thing in 2.8. So you can copy it from there. Is that okay? Bing Yao? Bing Yao. Are you there? I will go write the proof for the sup equal to minus n. No, I know I didn't prove it, but I will go write it down in the notes. Yeah, I'll go write it down. Okay. Anything else? Could you scroll to the end of the last? Sure, yeah. Here? Yeah. I mean, the notes, we will upload them, so you don't have to write down anything. All the notes are getting uploaded on Quarkus. Yeah, yeah, we always upload them. All right, good. So if you don't have any questions, I'll close it.